one. So last time when we stopped, we actually got extremely close to the solution. If we see like these lines of code here, that's all we really needed to finish the entire thing. We were like so very close. I just didn't understand how to solve this last problem. Uh, and a little update in that regard. So we're first gonna explain what this code is, but I actually only figured out this code 30 minutes before the stream started. And because I was trying to explain why this code wouldn't work, so I tried solving it and it did work. So that's pretty funny. So during the week, in between this video and the last video, I ended up going into a 5-hour proof session where I figured out an alternative way of solving everything. So I will discuss the two different ways and compare them a little bit. I do think this method is a lot nicer because it's a lot shorter. We were very close. But both of the versions are equally as good in defining this algorithm. So in this lemma right here, we're trying to convert from a path between A and B, where you're allowed to travel through any edge, into a path here that goes from N to B, that disallows any paths from A, but you travel from A to something else to begin with. So what are the, in the backwards direction, we were pretty easy, just construct it from path not into a path. If we have a path that doesn't contain the letter A, the node A within any of its nodes in the path, then we can easily build a path from that. That's just converting backwards in that regard. But the difficult direction is the forwards directions, where we have a path and we're trying to prove that you could exclude the node A from that path. But as everything, we will just do induction on P, and I will, this brings us into two different cases here. The first case is that P is just the reflexivity, basically if the path from A to B is just the path from A to A and B is equal to A, that is one possibility. But we have the assumption that A is not equal to B, so that possibility is impossible. So we have this N is not equal to N, so we're just done by contradiction. So the actual case that we need to think about is this case here. And I believe we did see this statement here last time. And this is where I got a little bit confused. And to be fair, this is very counterintuitive. So our induction hypothesis, it needs the assumption that N is not equal to from E. And then we can recover the induction hypothesis. So let's try explaining this with an example. So we're going through our list. We start with N, and then we go A, B, C, D, and then we have a from E, and then a to E. So this is our original path, and so we have a path from N to from E here, and then we have an edge E that's from E to E. And what do we do here? This is we're trying to rebuild a path that doesn't travel through N in any of these. And the N is like only traveling down this one edge, and then there's no ends down here. We need to prove that A is not equal to N, B is not equal to N, C is not equal to N, D is not equal to N, and all of these are not equal to N. So we're doing an extra check here. As long as n is not equal to from e, then we can append the 2e to it and get that this statement holds. So we don't know that n is not equal to from e, so let's do the two cases of this separately, because we could check. We know that it's either equal to or not equal to from e by the decidability of nodes, which is an assumption that we have. So we destruct on that, and we have two cases, one case where n is equal to from e and one where it's not equal to from e. Let's start with the second case where n is not equal to from e. Then we can plug this into the induction hypothesis here, as the input matches that there. And we get out the inductive hypothesis from that. It's basically converting from this thing here into a alternative path that might be shorter. Like, we don't actually know what path it's doing. It's just any different path, but it's a path not, so this question mark does not contain any n's. So we do the destruct, and we get n prime. I guess we call this n prime. So we have a path not from n prime to from e, and we also have an edge from n to n prime. I should call this a, actually. That makes sense. Yep. Yeah, so now that matches up with the a that we have down here. So we have an edge from n to a, which is this first one. And then we have a path from a to from e that does not include n. And we get that from the induction hypothesis on this path. Because this path is, we just needed to prove that n is not equal to from e, and then we get that this path can be converted into a path that doesn't contain n. And now we're just trying to append the 2e, no, from e, yeah. We want to append the 2e to it, because we know that there is a path from e to 2e. So let me add some dashes here. So we have this edge from n to a. Then we have a path from a to from e. Then we have an edge from e to 2e. And by our induction hypothesis, we're able to convert this path into this path here. It changes the part in the middle into some random thing that doesn't include n. And then we have a path not from a to from e. We still have the same edge from n to a. And we still have the same edge from e to 2e. So to solve this thing here, we just rebuild this structure here, and then we have a path not from a to 2e that starts with the edge from n to a. We just say that a is the correct one here. Exists a. Split auto, it already found the edge, that from e to 2e edge. No, I found the he edge, yeah. And now we just need to find path not. And so path not is just append this extra edge 2e to the from e. So like adding in this extra edge here. And we would be done by just doing auto. So that's that case. The other case is a little bit weirder. What if n is equal to from e? So now, going back to this example here, it's still the same structure, but we instead call this n, and this n. So we cannot recover the induction hypothesis here because this assumption here, the n is not equal to from e, is never going to be true because n is equal to from e, and you can't like recover the induction hypothesis from that. So we can't build it this way here. But just looking at this structure here, we're trying to recover a path from something to 2e that starts with an edge from n to something. So if we were to chop out this entire thing here and just keep this last n, like we could just delete all of this, then we have a path from n to 2e that starts with n, it goes down to a node, and then a path from 2e to 2e, which is valid because 2e is within the graph, and 2e is not equal to n, as we have as in our assumption. So in this case here, we just simply chop off all of this thing, we just ignore it, forget about it, and we're done by saying that we just have this edge here that matches up this edge, and then this path naught is just from 2e to 2e, just tell us we're done, we've reached the end. So let's do that. After doing a subst, we change the name n into from e everywhere, but we don't need this p anymore, we don't need this p, we don't need this ihp. The only thing that we care about is that we have this edge e that's from e to 2e, which fills in this thing here. So we'll say that the path is just from 2e to 2e, exists 2e split auto, and that splits it into these two goals. This one, it's basically an eta expansion of the e. We can just say that this from and to is how you built up the e. So you just destruct the e, and that will do the eta reduction. Then we want to prove that there's a path naught from 2e to 2e that doesn't go through from. That's pretty obvious. We just have reflexivity, and then we just to show that 2e is within the nodes of G, which is just true because we have an edge from e to 2e, and the edges are closed in the graph. So with that, we have completely finished the proof. Wow. It was very surprising to see that this is the only thing that we needed, and my 5 hours of preparation to do this in an entirely different way was entirely unnecessary. But yeah, I do think the alternate way is still pretty interesting, so we'll cover it after a few things. So what have we proven here? We've proven path decidable. Let me check to make sure that anything admitted? No. Any admits? Nope. No admitted and no admits. And let's check to make sure that this compiles all the way down to here. Yep, it is completely done. So we have fully proven that path decidable is true. And that statement is saying that for any graph G, if you have two nodes A and B, then you either have a path between these two nodes in the graph, or you don't have a path between these two nodes in the graph. So what does that give us? If we just do a print at the bottom, print path decidable, it gives us this gigantic proof here. There's a whole bunch of stuff going on, and that's pretty messy to look at. There's a lot of these EQ rect everywhere, and it just keeps going and going and going. There's a EQ int r in there. But all of these EQ int r and EQ rect, they don't have much computational value. It's just like stating that two things are equal because a proof says that they're equal. Pretty much the short description. But what we really care about is let's try like removing all of these EQ-ins and just extracting out what the code associated with this lemma is. Because in the constructive setting, we are able to prove stuff by stating that there's a piece of code that has that type. So let's figure out what that piece of code is, but not within Rocq, but within OCaml. And the really cool thing here is that Rocq comes built in with this extraction library. So if we import it, and then we do a little bit of suggestions here where we say that some bool should be mapped to the booleans within OCaml, and bool should also be mapped to bools within OCaml. That just does a little bit of simplification. And now we do this extraction path decidable, and let's ignore the error messages for now. We get out this much simpler condensed definition of path decidable. Expand it out. It's still long, but it's a lot cleaner than what it was if we just printed it out. Yep. So this chunk of code here matches up with the depth first search algorithm. This is the algorithm that shows up in all sorts of programming problems, interview questions. We have now formally verified that it works. So if you're ever in an interview where you need to prove, like, you need to write an algorithm in depth first search, and then your interviewer asks you how confident you are in your answer, you could say that, oh, I formally verified this. I formally verified depth first search. And that's a pretty incredible thing. We can have a very practical algorithm that is completely formally verified. Although it did take us a lot longer to write this. And this YouTube series has been, this is part 6 right now. But this is a fully verified depth first search algorithm. So now let's see what these error messages are up here. They're not actually error messages. There's just a whole bunch of things that are missing within our proof because we assumed them as axioms. So this first top part here is set to bypass opacity. That doesn't matter that much. It's just unfolding a little bit extra. So that's not really an error. The following axioms must be realized in the extracted code: node, node order, compare, node ordered EQ_dec. And that's basically telling us we never actually defined how we handle nodes in the first place, what nodes are. We've left it arbitrary. So those axioms of like just saying that node is this random thing, we need to provide it an actual value within OCaml. Let's just say we plug in node being the natural numbers. Then we can find this node ordered dot compare, which is just saying less than within the less than or equal to in the natural numbers. And then node ordered EQ_dec, basically saying that for any two natural numbers, there is an algorithm to tell us whether the numbers are equal or not. So node doesn't have to be the natural numbers. It could be something a lot more complicated, but if we just assign it to the natural numbers, then that would work. And whatever definitions that we have of this compare and EQ_dec, it also tells us here that you need to do proofs that they make sense, that they are actually a comparison function and a less than function, which we've just assumed as axioms, but whenever you define a specific definition of node, you would need to prove those axioms. So it's telling us that, well, we have everything done for an arbitrary set of nodes. Whatever type we use to define our nodes, that's going to be we need to prove all those lemmas about it. So let's look at this depth first search algorithm. why is it a depth first search algorithm? And let's match it up with how we define the proof, this final statement of path decidable. So we started out our proof with an induction on this G using our graph int function. It's basically converting this G into a whole bunch of smaller G's. Basically, to prove path decidable, we are able to use the induction hypothesis IH within here on a smaller subset of G. So we can find any path for any smaller subset of G, and we can use that to find paths within the larger subset of G. You could think of this as like, in order to do a path from A to B, you find a neighbor from A to N, and then you remove A, and then you find a path from N to B. You just are removing this node from the graph, and that's inductively smaller, so we get our induction hypothesis. So let's see here. The first step that we're doing here is checking to see if A is within G itself. This, of course, is like sometimes given to you as an assumption. It's basically stating that the A that we are starting at, our starting point, is within the graph. But if it's not within the graph, like if we see this S, if S is false, else, then we just return false. Because we know that if we can't even start within the graph, then there is no path within the graph at all. Then if we, starting with S is equal to true, we enter into this main chunk here. We recover the inductive call here as hrem. That's the thing that we saved here as this assumption, assert, as hrem. It even called it the same name, hrem. And this is our thing that we can query for any path within the remove node of the G. So if we just need to search within a smaller graph for some remove, for removing the first node A in that graph, then we can recover decide whether there's a path or not. Then this next step here, node order.eqdec AB. The first thing that we need to check is like, oh, we already started at A. What if A is equal to B? If so, then we're just done. We've the start point and the end point are the exact same. So any path is just like immediately done. We're just true. So if we find that this is true, we are done. And so we just return true. Otherwise, we know that A is not equal to B, and we enter into this thing here. And this is we're searching through all of the nodes of G, S dot exists, and we're trying to find this property on any of the nodes of G. This property matches up to finding a neighbor of A. So we see here that we see A to N. So we found a neighbor from A to N, an edge from A to N, which states that N is a neighbor of A. And then we can find a path from N to B within the graph that removes the A from it. So find a neighbor, then check if there's a path from that neighbor to the final node B. True, else false, for like finding that. And if we check through all of the nodes within G, then we have covered every single one of the neighbors. So if we manage to find any neighbor that works, so if any neighbor exists that has a path from that neighbor to B, then we're done. We return true. So like if B0, then true. If we've checked every single one of the neighbors and we fail to find any that have a path from that neighbor to B, then we return false. So that is our path decidable algorithm. It completely matches up with depth first search because we are going through going as far down as we can before. That's how we set up the inductive hypothesis. We're just searching in this inductive case on an immediate thing. And basically, we've converted from a large Rocq proof that proves that this path is decidable, that we can either find a path or not find a path, into a formally verified definition of depth research. And that's pretty cool. That's the main goal of this tutorial series. It's a tutorial series, but it covers a lot harder stuff than just a basic tutorial. But there's a side thing that I also wanted to mention. Let me first save this. Guess we don't need the to do anymore. So now I wanted to also showcase the alternate version that I wrote, which is on this separate branch. So in this version, I was really worried about like loops within the path. Basically, A, B, C, D, A, B, F, G. And here we have a loop from A to A, so we know that we can just delete it. Delete this chunk here, and we still have a path from A to G. But we could also have some paths within here that are not really associated with A itself. So even if we delete this path, that loop there, there's still this loop here that is entirely unnecessary. So we should be able to iteratively delete all of these loops. And if we delete all of them, then it also handles the case of deleting this one in the front, because this is also a loop. If we just take this path, we can find a path A, E, F, G, a simplest path that contains no loops. And that's what this proof is doing. It turns out that this is much stronger than we actually needed it, but it still works. Everything is really nice, and I'll showcase some of what the lemmas look like. So starting again with the very bottom of the yeah, this involves a lot more code. It's a lot more difficult to prove, but we still have the same path decidable at the end, whether there's a path or not a path. And in here, we instead go through the path convert function. And path convert takes us from a path into this path list. So what is this path list? Let's look at the definition of path list. So path list, it takes in an input G, which is the graph, and an L, which is a list of nodes. And this list of nodes represents the path that we take. So the L can't be empty, that's just false. But if we check if it's a X, if it's a singleton, then we just need to know that that X is within G, and then we have a path from X to itself just by being there. And in the other case where we're trying to append an extra edge, then we need to know that this edge from X to Y exists. that it's true, and that this y is like where that the remaining path y to L is a valid path as well. So this path list is basically taking in a list of nodes and enforcing this property of this list of nodes is actually a valid path by traveling through a set of edges within the graph. And if we were to ever want to return the actual path from the depth first search algorithm, you can just return the thing that this path list gives you out, and it would be that path that we found directly. So in addition, I created this start end. It basically labels the list node with a start and an end, basically saying that this list starts with B and ends with C. And if we append an extra A, then it starts with A and ends with C. And this extra lemma here, the definition here, postfix, it's basically telling us that this L on the left, the L on the right ends with the L on the left. So if they are equal to each other, then that is true. But we can also append as much as we want to the list on the right, and that would still work as long as we inductively have that it's a postfix. And with all of these statements here, we're able to do a whole bunch of theorems to prove that we can recover from any path, we can recover a list that has no duplicates in it. So let's look at that final lemma. It's a combination of two lemmas. So the first lemma is path convert. If we have a path from A to B, then we have a path list that corresponds to it. There exists a list that has the same start and end as A and B, and it's a valid path list. So that's this lemma here. And scrolling down, this is combined with this path unloop. I added a link here because I copy pasted this line here, how to do induction on this L. I definitely could have proven it myself, but it was easier to just copy paste that line. That's why there's that statement there. Then this is stating here we have a path list L, and we would like to recover a path list that has no duplicates in it. So we start with a list that could have duplicates, and we remove all the duplicates inductively. And moreover, this list that we recover is a subset of the other list. It's like it didn't just come out of nowhere. We recovered it from the smaller list, the larger list. And it has the same start and end of A and B. It's L. So using those two lemmas, we were able to, this is another convert function. So those two convert functions were used within path decidable, path convert, and then path list convert to basically take us from a path into a path that has no duplicates, and then we're able to call the induction hypothesis and everything to get everything that we want out of this. Within this whole thing, the one lemma that does remove the duplicates is this lemma up here. Let me find it. Yep. So in split is for any list L, if A is in L, then we can recover an L1 and L2 and basically take this L and split it up into L1 and L2, where A is the last element, like the last time that we see A in the list, so that means that there is no A in L2. So we just chop off this entire front of the list, and we're left with just the remaining part. And if we do this iteratively over the whole list, then we've cleared out all the duplicates. So that is pretty cool. It's pretty complicated, and it took me 5 hours. It also involved a lot of postfix manipulations. So yeah, but this, if we scroll all the way back down to the bottom, pathless convert, pathless split, pathless remove, path decidable. Yeah, so we go back to path decidable, scroll down even more, get to the end here. And now we check the extraction again. We check in here. And this matches up exactly to what we had before. So even though the proof changed, the program itself, the thing that we're extracting out, maybe it does look a little bit different. No, never mind. It only looks different because I had a different length there. The code that we got out here is exactly the same as the code that we had before, because the only real difference between that is how we did the proof. It's not the structure of that proof itself. So yeah, I will soon let both of these things be available on GitHub publicly, and I will also create a summary video. I'm not sure if it will be next week or if I will do it live or separate, like pre-recorded. But there will be a summary video about this whole process. Hopefully, it will make it a lot easier to understand a lot of these things in a very condensed way. And yeah, I will find more interesting things to prove like this. Maybe even more things about graphs or some other proof entirely. Yeah, I think this marks the end of my tutorial series on proving path decidable, and yeah, I'll see you guys for the next video.